Okay, so we're going to talk about Dalton's laws of partial pressure, okay? Sounds kind of scary. If you'll remember, John Dalton was one of the people we talked about at the beginning of the year that discovered the atom. But now we're going to talk about his work with gases. And he said in a mixture of gases, each gas has its own partial pressure. And that contributes to this whole pressure, the total pressure, okay? So the total pressure equals the sum of the individual partial pressures. It's a pretty easy concept. I'll show you how it would look in an example. So if you have air, air is made of several different gases. You've got nitrogen and oxygen and CO2 and some other things. But let's pretend you just have a sample that contains only those three gases. So the total pressure of the sample is 760 millimeters of mercury. And the partial pressure of carbon dioxide is 0.285 millimeters of mercury. And the partial pressure of nitrogen is 593.525 millimeters of mercury. What is the partial pressure of oxygen? So this is pretty easy. It's just parts, right? So you have the CO2 plus the nitrogen plus the oxygen is going to equal the total pressure. So however you would like to write this out, I think the easiest way to think about this problem is to, instead of doing an addition problem and then a subtraction problem, I think it's easiest to just do a subtraction problem, right? 760 is the total. We know that 0.285 of it is carbon dioxide and 593.525 of it is nitrogen. So we get a partial pressure of the oxygen of 166.19. And if you want to really take sig figs into account, there would be actually a zero there for that partial pressure of oxygen. Okay, so this is actually a pretty easy concept that I'm going to use to do a really annoying thing. All right. So today we're going to talk about collecting gases. If you'll recall, we've done something before where we've taken baking soda and vinegar and we collected gas in a plastic bag and you tried to fill that plastic bag. But what instead would happen if I asked you the question, how much gas does this reaction make? What they do is they actually collect gas over water. So you'll have some sort of reaction happening, okay, if you'd like to visualize baking soda and vinegar, because we've done it before. The gas comes out, there's a stopper here, it comes out a tube, comes through this tube, and then it gets collected in something else, a test tube, a bottle, an inverted graduated cylinder, something called a eudiometer. There's a lot of different places that you can collect the gas, and you'll see that in a video today. And this is actually how they collect gases. All right, the problem is that when they collect the gas, right here, this collected gas is not quite pure. There's actually water vapor mixed with it. So you have the pressure of the room, the pressure that this gas is under. Remember, the room is pushing down here, and that's what's creating the pressure up in there. But you also have the pressure of the water vapor that's mixed with it. So when we collect this gas, we have to take that into account. So to get the pressure of just the gas you're collecting, just the CO2 or just the oxygen, whatever it is, you need to subtract water vapor's pressure. There's a table of water vapor pressure on Google. There's probably 100 of them. I have one for you right here that you can look at from your notes. It's also attached to the lab today. It just says water vapor pressure is what it's looking at. And it's got degrees Celsius up here. So you need to know the temperature of the room. And then it tells you the pressure of water at both millimeters of mercury and kilopascals. If you have to Google this, you might find it in Kelvin, you might find it in ATM, so just pay attention to your units. what this says is if I collect gas in a room that is 20 degrees, then water is going to put off a pressure of 17.5 millimeters of mercury, which doesn't mean much to you right now, but I'll show you how we're going to use it. So for example, if you had this, this collection device that I was just talking about. So you have some, test tube, and that test tube is, creating oxygen gas, and the oxygen gas is coming out and it's going through a tube and it's getting collected in, an upside down beaker that contains water or something. You could collect that oxygen gas and find out that you've got 755 milliliters of oxygen that's collected. Now, what's important about gases we know now is temperature and pressure. So it tells you that the temperature that it's collected at is 25 degrees Celsius, and the pressure of the room is 748 millimeters of mercury. Maybe there's a storm rolling in, so it's a little bit below standard pressure. So then the question becomes, what would the volume of that pure oxygen be at STP? And you might be asking yourself, why do I care? Why would I ever care what the volume is at STP? Well, you care because stoichiometry is not dead. It's here till the whole rest of the year. So we need to think about the room, what it's like in the room. And in the room, there is a pressure of 748 millimeters of mercury. And the volume, again, this is what happens in the room that I'm in here. The volume collected is 755 milliliters. And the temperature of the room is 25 degrees Celsius, but we don't ever use Celsius for gas laws. So it's going to be 298 Kelvin. Well, the question says, well, what would it be at STP? So at STP, right, the pressure would be, this is P2, would be 760 millimeters of mercury, right? That's the STP value. The volume, this is what I'm asking, V2, what is the volume? And T2 would be the temperature at STP, which is 273 Kelvin, or really cold, 0 degrees Celsius. So I'm all set up here, right? Because I've got this sample and it's collected, and here's what it is at the room, and I want to know what it's going to be at STP. But I've got one more little finicky thing to not forget about: the partial pressure of water. If I'm collecting oxygen gas, that's all fine and dandy, but I need to subtract the partial pressure of water. So 748 isn't going to be enough. The temperature is 25 degrees Celsius. So I need to go back to this table here and find out at 25 degrees Celsius, what is the partial pressure of water? And it turns out it's 23.8. So I need to subtract that. Okay, so 748 minus 23.8. Is that what it was? I already forgot what it was. Okay, so I put 748 minus 23.8. Is that what it was? Equals 724.2. That's kind of my new pressure, okay? Because I have to think about that partial pressure of water. Woo! So that was a lot of work just to end up back at a combined gas law problem. So here it is. You've got combined gas law, P1 V1 T2 equals P2 V2 T1. We need to solve for V2, so divide by P2, divide by T1, divide by P2, divide by T1. I like to rewrite these because it bothers me when it's written like that. So I write P1 V1 T2 over P2 T1. That way, when I rewrite it, it's a little bit easier to put into my calculator. So I just go ahead, I plug it in here, plug and chug, right? 724.2 is P1 times the 755 milliliters that I collected times T2, 273, divided by 298. That's the T1, divided by 760, okay, equals 659. So what I just found here is I found out that I did an experiment in a room and I collected 755 milliliters. But if I had done that same experiment perfectly at STP, I should have collected 659 milliliters. And the reason is stoichiometry. It's so that we can use stoichiometry. Okay, so here is what I just wrote out. This is in your notes. I post all the notes. So if you really want to see them like this, you can. The only thing that I caution you against is this is written where the numbers are plugged in. This may be more comfortable for you, but I talked to AP chemistry teachers and AP physics teachers, and this is kind of the mamby-pamby way to do it, and you should be rearranging the equations first. Okay, so this is like the lab today. This is like the why I care, right? So if I've got baking soda that I'm decomposing, it's very, very, very exciting. You're turning a white powder into a white powder. It's super exciting. And it puts off a little bit of CO2 gas. It decomposes like this. 2 moles of this make 1 mole of each of these. So if 2 grams of baking soda are heated, what is the theoretical yield of CO2? Your stoichiometry brains should all of a sudden be going, all right? You should be thinking, okay, fine, I've got 2.0 grams of baking soda, and I'm gonna go to blah, 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 and I'm gonna end up with 22.4 liters per 1 mole of CO2, okay? And I ask you, what assumptions are being made, okay? You are assuming when you do this, that this is being done at standard temperature and pressure or at STP, okay? When you do stoichiometry, you assume STP. Life doesn't happen at STP, which makes these problems really exciting. In this one trial that we have 2 grams of baking soda. So let's start out with our stoich. 2.0 grams of NaHCO3. First, I have to go from grams into moles. Not going to waste your time on this. I'm just going to tell you the molar mass of baking soda is 84 grams. At this point, you can Google it and find the molar mass of things if you still don't know how to find a molar mass of something. Then I'm going to compare using the balanced chemical formula. Remember, there were 2 moles of this. This is back to the balanced chemical formula to every 1 mole of CO2. Okay? For every 1 mole of any gas, there are 22.4 liters of any gas. So I put this into my calculator. 2 divided by 84 divided by 2 times 22.4. Voila. So I get a theoretical value of 0.27 liters. I tried to keep my sig figs intact. 2 sig figs, 2 sig figs. All right. This is called a theoretical value. My theoretical value, what I should get. And my theoretical value, remember, happens at STP. But as you can see here, this entire lab does not happen at STP. Instead, it's happening in a room. So I've got the pressure of the room is 750 millimeters of mercury. Let's not forget to subtract the partial pressure of water. Partial pressure of water at 20 degrees Celsius is 17.5. Go back here, subtract, because that was the temperature. the temperature was 20 degrees. Never do the labs at standard because standard temperature is 0, which is very cold. My volume is 210 milliliters, and my temperature is 20 degrees Celsius or 293 Kelvin. So that's at my room. And then I always say, okay, fine, this is a STP. And I label these just because I think it makes it a little bit easier. So at STP, it's 760. And the volume is what we're looking for. And the temperature is 273 Kelvin or 0 degrees Celsius. So here we go. I told you that formula would come in handy. I've already done it once. There it is. I don't have to redo it again. All right. So don't do more work than you have to. So when I plug this in to find V2, I find 750. Oh, sorry. I made my own mistake here. Don't forget to use 732.5 times 210 times 273 divided by 760 divided by 293. Okay, so I get 188.5. So my V2 equals 189 milliliters. We call this the actual amount or the experimental amount, what I actually found in an experiment. So now I get to my very last step. If I possibly have any colors left, my percent yield is equal to actual divided by theoretical times 100. So I get the actual 189 divided by my theoretical. My theoretical is in liters and my actual was in milliliters. Don't forget to convert that. That's 270 milliliters. So I got to put 270 down here times 100. So my percent yield is 189 divided by 270 equals 0.7 or 70%. And I'm maintaining my sig figs all along. I do end up with 2 sig figs because of that 270. All right. They're evil. They're long. There's a lot of things to think about when you're doing these, but they're definitely doable.